This is the SUPA Cormac astronomy meeting, or the culmination of it, because the meeting took place during the whole of today, and I have to say I've been here from the whole of today from the very beginning, and we've had something like, I think, about 80 hugely enthusiastic, very amazingly gifted young people talking about their subject. I think that the poster display was outstanding. I think the presentations, John, were absolutely excellent. So we've got this rising generation of really bright young people to follow on, follow in the footsteps of the distinguished astrophysicists who exist in Scotland. Just a word about Suzanne. Came to the UK from France in 1996, studied physics at Imperial College in London, and did a PhD in astrophysics at the Institute of Astronomy in Cambridge, and then went for 3 years to the University of Essex, and is now in University of Oxford since 2010. And she works on the detection and characterization of extrasolar planets, planets that are outside our solar system, via what it says here, the transit method. I'm a microbiologist, so I'm adapting very quickly to this. Transit method, and on exploration of the time domain in astrophysics in general. She's particularly interested in finding and studying small terrestrial or even Earth-like planets and young planets. So we look forward to hearing all about that. But before that, let me tell you about the bequest, because the Cormac bequest, this society, which was founded in 1783 and is unique in the United Kingdom because it covers all disciplines: science, engineering, mathematics, logic, the arts and humanities, history, public services. The 1,500 fellows of this society cover all these and more subjects. And that is because the charter which was endowed to us by the King said that we were set up for the advancement of learning and the advancement of knowledge. And our predecessors chose to interpret that as meaning all knowledge. So it is rather unique in that regard. Anyway, Robert Cormac, he was a Scot. He was born in 1858 in Anstruther. His family was connected with the fishing industry. When he was 8 years of age, the family returned to the town of Eyemouth. His mother was a native of that place. He attended a public school there, and at the age of 14, he applied for a post in a firm called Charles Jenner. Charles Jenner's is still the name of one of the most famous department stores in Edinburgh. So he was associated with this. He rose to be a partner in the company, and when he retired, took up astronomy as a hobby. And when he died, he left his bequest to this society for conduct in the research and learning in the field of astronomy. This society depends on bequests like that, and I think it's fascinating that we have had events almost every year since he made this bequest, and there are 12 recent lectures in successive years on the subject of astronomy here, as we have tonight. So that's the background, and without further ado, I'm going to ask Suzanne to present her lecture. Welcome, Suzanne.
Thank you very much for that introduction. Whilst my projection... Right. So I'm going to tell you tonight a little bit about the work that I and my colleagues do on searching for and characterizing planets around other stars than the Sun, i.e. exoplanets. And I was extremely fortunate to start my PhD in 2001 when the nature of the first exoplanets had just been confirmed in a very dramatic way, as I'll discuss a little bit later on. That really brought the field from almost what might have seemed like a pipe dream to a real endeavour of physical characterization. And what I'm really interested in is putting the Earth in context. So the previous slide had a doctored version of this very famous photograph, which I notice is also in the hall, which is Earthrise, seen by the crew of the Apollo 8 mission in '68. And really this view of the Earth as just another planet, one potentially of many, is the kind of view that I would really like to substantiate by exploring the full diversity of the exoplanet population in the galaxy. So I'm going to start off by going through some of the properties of the planets in the solar system, because they are, after all, the best studied planets, and they give us a frame of reference for interpreting the much more sparse information to which we have access when we're studying other planets than those. So this is a composite series of images of the now 8 planets in the solar system, where the sizes are to scale, although obviously the distances are not. And you can see the sun on the left. I'm just going to use this. Right. And so a number of characteristics come to the fore when you look at this composite image. One of them is that the planets fall broadly into 2 categories: smaller, primarily terrestrial planets in the inner part of the solar system, and larger planets mostly composed of gas, namely hydrogen and helium gas, in the outer parts of the solar system. Another important properties of the planets, and one that tells us about the way in which they formed, is that although only about 1% of the mass of the entire solar system is in the form of planets, so the Sun contains 98.5% of the mass in the solar system. Jupiter contains 1%, and the rest is shared among the remaining planets, but they all have very tiny masses in comparison to the Sun. But on the other hand, almost all of the angular momentum, the spin, in the solar system is in these planets. And the formation of planets is a necessary step in allowing stars to form. And so that's one of the reasons why we expect to find planets around many stars. The planets are needed for the stars to be able to accrete all the material in the cloud from which they form. And we'll go over that in a little bit more detail in a moment. Now, if we look at the orbits of the planets in the solar system, this is a top-down view of the orbits of the inner planets. So you've got Venus, Mercury, Venus, Earth, and Mars. A schematic representation of the asteroid belt that lies between the orbits of Mars and Jupiter. And if you zoom out further, you've got the orbits of the outer planets, along with this second belt of smaller objects, which we call the Kuiper belt, and Pluto is a member of this Kuiper belt. Now, this is an example of an asteroid that came rather close to Earth about a year and a bit ago. And the asteroids and the Kuiper belt objects also play an important role in our understanding of how the system formed. In particularly, the Kuiper belt objects are teaching us quite a lot about the conditions in the initial conditions in the solar system when the planets were forming. Another important component of the solar system is the comets, some of which come close to the Sun regularly. Halley's Comet is the best known of those. So observations of Halley's Comet have been recorded since ancient times. And it's the brightest of the so-called short-period comets, the comets that come back near the Earth very regularly and near the Sun. However, many more comets actually spend all of their time in the outer parts of the solar system, and if they do come near the Sun at all, it is only once every few thousand years. We think that there is actually a cloud, a roughly spherical cloud, of comet-like bodies orbiting around the Sun. It's a very diffuse cloud, and you wouldn't be able to see it just by looking out. But that, again, is one feature which we might be able to look out for around other stars than the Sun. Now, on the basis of observations of the solar system planets, and the asteroids and some comets, then a theory had been constructed as early as the 1700s for the way in which the solar system formed. It's known as the nebular theory, and it was developed primarily by Swedenborg, Kant, and Laplace. And I'm presenting it here today because the basic building blocks of this theory still hold sway today. So the idea is that stars form from a cloud of dust and gas, and we see evidence of such clouds in the galaxy around us. And within these clouds, there may be regions which are slightly overdense for one reason or another, and they will have a stronger gravitational pull than the neighboring regions, so they will gradually start to collapse in on themselves. But if there is any angular momentum in the cloud, if there is any spin or turbulence, then that is a quantity which must be conserved, and so when the material falls in, it would also start to spin faster, in the same way as you've probably seen ice skaters spinning and pulling their leg in, and that makes them spin faster. Now, one way of getting rid of this angular momentum is for the material that is falling onto the star to form a disk. And then the material can very efficiently transport angular momentum out, whilst, so a small fraction of the material remains in the outer parts, most of it falls in. And the star forms from the infalling material, whilst in the disk, any local overdensities will themselves go on to form planets. Eventually, the temperature and density in the core of the star are high enough that it ignites thermonuclear fusion reactions. And in the process of doing that, it will start emitting light much more forcefully and of higher energies, and that will have the effect, among other things, of dispersing what remains of the disk, so that you're left with a star surrounded by a set of planets. Here, the inner planets of the solar system have been represented. Now, we've known for a long time that all the other bright dots in the sky are probably stars like the Sun, at least most of the ones we can see with the naked eye. And this is a diagram rather than a photograph that was put together by astronomers at Lund Observatory, in which every single dot is a naked eye visible star. And, but of course, the size of the dots is proportional to how bright they are. Now, there's about 100 billion stars in the Milky Way, and approximately of order 100 billion galaxies in the universe. And each of those is a sun like our own, with potentially a planetary system around it. So there's strong reason to expect that if we don't live in a special place, then there might also be planets around them. In fact, with the advent of infrared astronomy, particularly in the 1990s, we started to be able to get pictures of the star and planet formation happening in situ by looking at these beautiful nebulae. This is the Orion Nebula. So these are stellar nurseries where stars are in the process of forming from the cloud of dust and gas, which I described earlier schematically. And so the bigger and brighter stars at the center of this cluster are in the process of blowing out the material around them. So the radiation which they emit is blowing the material out and forming this shell. And at the edge of this shell, the material is shocked into denser regions, and that creates a chain reaction in which other stars start to form. Now, if you look in this cloud, you can see regions where you have stars in the process of forming which are embedded in their own little mini nebula. And in some cases, we see them in silhouette on the background of brightly illuminated dust and gas. And if we zoom in on this one up here, you can see a feature seen in profile, and this is actually looking at a planet-forming disk in profile. It looks darker along the edges than in the middle, because in the middle we're looking straight at the star, whereas along the edges we're looking through the dust. And there's now been hundreds of these so-called proplids identified, and we have other ways of detecting the presence of disks around stars. So we know that certainly the conditions are there for the planets to form. Before we go on to look at methods by which we detect exoplanets today, I want to take a quick look at the way in which some of the solar system planets were discovered. The inner planets and all the way up to Saturn are visible to the naked eye and were identified without the use of telescopes. However, the discovery of Uranus didn't occur until the late 18th century, and it was made by William and Caroline Herschel, who were actually looking for comets. So they were looking for new objects which appeared in the sky and which moved relative to the other stars from one night to the next. And they noticed such a moving object, but by charting its position over the course of approximately a month or two, they were able to work out that actually it wasn't a comet, it was another planet. And this is a somewhat more recent image of the planet Uranus by the Hubble Space Telescope. It's actually a composite of 3 images taken at 3 different times, which is why you can see here 3 of the moons of Uranus, and on each of the image, the little moons have moved a little bit. The discovery of Neptune is even more intriguing because it was discovered as an unseen body which perturbed the orbit of Uranus. So, over a century of observations, the orbit of Uranus was estimated quite precisely, and people were making predictions for where it should be on a given night in the future. But these predictions were always somewhat off, so schematically speaking, the position might be predicted to be here, but then the observations would find it to be something slightly different. And 2 mathematicians, the British Adams and the French Le Verrier, predicted at about 1 year's interval that that must be due to the presence of another planet further out than Uranus. And they were able to make predictions for where we should look for this additional planet. However, at the time, the power of mathematics to describe nature was not quite so well established as it is today. And it was actually very difficult for them to convince astronomers to go and look for this planet. And in the end, Le Verrier managed to convince a German astronomer called Galle to observe this planet. And he found it at the predicted position. This is again a Hubble Space Telescope image of Neptune. And it's actually a story of missed opportunity for the British astronomical community, because there were actually somewhat half-hearted attempts to observe the planet when Adams predicted its existence, but the observations were not successful because the predictions were misinterpreted. It wasn't even a problem with the math. Now, if you're looking for a planet around another star, you have a difficulty because planets emit almost no light of their own, and we only have access to the observable universe through light or through a number of more exotic forms of radiation, which I won't go into today. So one of the things you can try and do is just look for the light from the planet. It might take 2 forms. Some of the starlight received by the planet is reflected. The planet also might absorb some of that starlight and re-emit it in the infrared. And actually, for most of the scenarios we can think of, it's in the infrared that we would have the best chance of finding the light from a planet directly. Unfortunately, planets, by definition, are rather close to their host star. So you have the difficulty of having to cancel out the light from the host star to look for the possible pinprick of light from a planet near it. And so this is an image taken with the Gemini telescope on Hawaii of a nearby star a few times more massive than the Sun. And this little bar here shows 40 times the size of the orbit of the Earth around the Sun, 40 astronomical units, at the distance of this star. So even if we were able to perfectly cancel out the light from this star, we would still have to look very close in order to find planets where, at least if they are at the same positions as the planets in the solar system. For reference, the orbit of Neptune is about 30 astronomical units. These hexagonal features which you see here and all of these little speckles are due to imperfections in the optics and to diffraction caused by the structures which hold the mirrors in place of the telescope. Now, we can model these quite well, and in fact, this is an image which first of all, it's been zoomed into this smaller square here, so the same bar is now half the size. And then the astronomers who took this image, who were basically Canadian, American and British team did the best they could to subtract the light from the star. And it's impossible to do a perfect job of this. You can see there are some speckles. They've been color-coded in 3 colors because the same system was observed at 3 different times in order to see if, and these 3 sets of observations were taken with essentially the telescope instrument rotated in a different orientation on the sky. One would hope that most of the instrumental imperfections go with the telescope and the instrument, so they would move relative to the sky when you do that. And indeed, you can see that the speckles that are seen in blue are not the same as the speckles which are seen in red. On the other hand, there are 3 dots here, which are at the same position in the 3 images. The reason they appear red is because the red color is the one that's been overlaid last. And these are, in fact, planets orbiting around this central star. They are relatively massive planets with masses estimated to be about 8 to 10 times the mass of Jupiter. Again, the star is also somewhat more massive than the Sun, and you can see the distances are quite large too. Even the innermost planet is somewhere near the orbit of Pluto in the solar system. But, so this is really a scaled-up version of the solar system, if you like, seen face-on. This picture was taken in 2008, long after the first detection of the first exoplanet. I'm showing it first because it's the most direct detection method. One of my colleagues at the University of Exeter was on the team that made the discovery, and one day she came into my office very excited and showed me this photo, and it was the most exciting. I mean, I shouldn't say this because I work on completely different methods, but this was the most exciting photo I'd ever seen. You know, this is the first picture of another planetary system. And I'm afraid that's the last pretty picture I'm going to show you. Because everything else we do is done indirectly, because we can't see the planets. So the method by which most of the confirmed exoplanets have been found to date is known as the radial velocity method. It consists in looking for the small wobble in the star's position as both the star and the planet orbit around the center of mass of the system. And the orbit of the star is absolutely tiny. In fact, it's much smaller than the radius of the star itself. The way in which we detect it is not by measuring the position of the star very precisely. We will try and do that in the next few years. But we can actually detect much smaller motions using the radial velocity of the star. That's the motion along the line of sight. And we measure this by putting the light through a dispersing element. Generally, it's not a prism, but it might be a slit or a prism. And we obtain a spectrum of the star where we see light of all different wavelengths, all different colors, with dark lines at specific wavelengths where elements in the atmosphere of the star, such as hydrogen or helium, have absorbed light at these very specific wavelengths. We know where these lines should be in the spectrum very precisely from laboratory experiments, for example, or we can calculate them theoretically for simple enough elements. And we can compare that to the position where we see them. In the same way as when a train is coming towards you, it sounds higher pitched, and when it's going away from you, it sounds lower pitched, the Doppler effect. Then when the star is moving towards us, the lines are shifted towards the blue, and when the star is moving away, the lines are shifted towards the red. So if we monitor this star, we will see its lines shifted towards the blue first and then towards the red. And if the orbit is circular, what we'll see is a sinusoidal pattern, something like this. And this is actually the data for the first discovery of an exoplanet, which took place in 1995. And it shows the radial velocity of the star in meters per second as a function of orbital phase. So basically, between this point here and this point here is a year for that planet. The planet's gone round its orbit once, and so the star has also gone round its orbit once. The first thing that's remarkable about this is how small that motion is, 50 meters per second. A star like the Sun is, I've got to get the numbers right, 100 million meters across. And so we are able to measure the position of its center of mass to a precision of a few tens of meters. In fact, this has gone much, much further than that in the interim. We can now measure the positions of stars to precisions of less than a meter per second. I mean, the velocity. The other thing which is very striking, and which is not really shown on that diagram, is that it takes only 3.5 days for this planet to complete its orbit. One of the reasons why it was not detected earlier than this, the technology existed for some years before this detection was made, and given it only takes a few days for the planet to go around the orbit, we could have detected it sooner. But nobody thought they would find planets so close to their stars. And in particular, not a planet like this, you can work out from the amplitude of the modulation what the mass of the planet is up to a factor which is to do with the inclination of the orbit, which we don't know in this case. But this planet actually has a mass similar to that of Jupiter. So it's a planet like Jupiter, but in the innermost parts of the solar system. We thought that planets couldn't form there, and nobody thought to look there until somebody basically, Mayer and Kellos, did a systematic search for whatever the data might show them, regardless of any assumptions they might have about what was in there. So that brings up a very intriguing kind of object, something that we call a hot Jupiter, which is a planet with a mass similar to Jupiter, a composition that's also probably similar, so primarily gas, but it's very, very close to its star, and the side of the planet that faces the star is irradiated incredibly heavily. So if we think in terms of the amount of energy received by the planet from the star, it's thousands of times more than the Earth and than Jupiter. The proximity to the star also has another effect, which is that the planet is the same side of the planet that always faces the star, much like the moon is tightly locked to the Earth, and we always see the same size of the moon. That means that we have a very strong, potentially, temperature difference between the day side and the night side, and that's expected to cause very violent weather patterns on these planets, which we're only starting to be able to probe, and that will be the end of my talk. The method which I work on, which is breaking my... there we go. It's called the transit method. And the transit method consists in looking for the small dip in flux that occurs when a planet passes in front of the star. So you have to be lucky to see it, because it will only happen if the orbit of the planet is aligned just right. But what's really interesting about it is that the depth of the transit tells you the size of the planet relative to the star. You also know the inclination, and so with a radial velocity measurement you get the mass, and if you put the two together, you get the density of the planet. The first transit was observed in 2000. That's the event which I referred to at the beginning of my talk, which really confirmed that these objects were planets, because before that there was a possible uncertainty about what the true mass of these objects were. But you can see this is a transit of another planet called HE 209458b. Again, it's a hot Jupiter. It's got a mass similar to that of Jupiter, a little bit less. It's got a size a little bit bigger than Jupiter. You can see the transit depth is about 1.5%, and that's typical for these planets. It lasts a few hours. And one of the really nice things about transits is you don't need very big telescopes to observe them, particularly if you're looking for transits around bright stars, which are very... it's useful to have transits around bright stars, because then you can do lots of other observations. This is the instrument that was used to detect this transit, together with Tim Brown, who was the person who built it, and Dave Charbonneau was the then PhD student who did the observations and initial analysis. And so it's a 10-centimeter telescope. It's the kind of thing that many a dedicated amateur might well have in their back garden. And in fact, still today, we have many dedicated amateurs who make very significant contributions to the field. So today we know of about, right, the number is fluctuating, well, increasing very rapidly, and what a true number is depends on who you ask and what they consider to be a confirmed exoplanet. But if I take as my criterion a planet for which we have a good idea of what the orbit is, and ideally the mass, then we have of order 800 exoplanets known today. And this diagram shows them on the plot of planet mass and Jupiter masses versus orbital distance from the star in astronomical units. And so the Earth is at 1 astronomical unit from the Sun. Jupiter is of order 1 Jupiter mass. Obviously, it should be exactly on that line. You can see I made that diagram with a little bit of hurry. But what's one important fact about this plot is that both axes are logarithmic. So each of these thick graduation corresponds to a factor of 10 increase. Now, you can see where we've discovered planets in a very wide range of masses, including some which have masses very similar to the Earth. And we're also finding them very close into their star and all the way out to the orbit of Jupiter and further. There are also the direct imaging planets which I was talking about before are somewhere out there. I haven't shown them because then you would basically not be able to see the detail in here. The current observational limitations of the radial velocity and transit methods are, well, the radial velocity method is shown here. The transit method is currently still sensitive only to shorter periods, but pushing out towards these longer periods. But it's starting to reach even smaller planets. The dark points here are planets which were discovered by the radial velocity method, and the red points are planets which were discovered by the transit method. The transit method, both methods are more sensitive to planets close to their star, but the transit method even more so, which is why you see most of these red points here. One of the interesting points is all the points which are surrounded by little green circles are members of multi-planet systems. So they are cases where there's more than one planet around the same star. And we've now, as you can see, found many of them, particularly the relatively low-mass planets seem to be primarily found in multi-planet systems, and that's a very interesting fact. The transiting planets are particularly interesting, as I said, because we can measure them, their radius as well as their mass, and this is again a similar diagram, but now mass is on this axis and radius on that one. And you can see all of the transiting planets for which we have good estimates of the masses. And this is a line which shows the theoretical relationship between radius and mass that you would expect from a pure ball of hydrogen and helium gas. And it would apply at higher masses to low mass stars as well, to brown dwarfs, which are stars which are not quite massive enough to ignite thermonuclear reactions, as well as to some of these giant planets. If you extend this line up here and put the data we have for stars, there's actually a very good one-to-one match, pretty much, between theory and observation. If you know the mass of the star and it's not a particularly evolved star, then you can predict its radius to fairly high accuracy. On the other hand, you can see that in this region, which corresponds to these hot Jupiter planets, there's a huge range of radii for the same mass. The difference is particularly strong in this mass range where the difference can be a factor of 2. What drives that is irradiation from the host star, in part. The irradiation heats up the outer part of the planet and makes them puff up. And the other factor that goes the other way is if the composition is not just hydrogen and helium gas, but if there is also a core of rocks or ices inside the planet. And here I've drawn other lines which would correspond to a pure water or water ice planet and a pure rocky planet down here. I should say the Earth is somewhere down here. So again, we have this population of hot Jupiters, and we're starting to unearth a population down here, which we call hot Neptunes, because we can tell from their location in this mass radius diagram that they have compositions which are probably similar to that of Neptune. And I'm just going to briefly outline the detection of the first transiting hot Neptune, which happened some years ago now, about 5 years ago. It's called Gliese 436b, and it was found by the radial velocity method. So we had a good idea of its mass, but we didn't know its radius. And so at the time, this is a diagram that was produced at the time by Greg Laughlin, who's an astronomer at the University of Santa Barbara, who has a very nice blog about what's going on in the planetary community. And he showed that different compositions, this is a primarily rocky composition, this is a primarily water ice composition, will give these two very different radii. And then he's just shown Jupiter for comparison, which is mainly gaseous. And some of my colleagues went and observed this, because they had nothing better to do one weekend, with a small telescope that's mainly dedicated to outreach in Switzerland. And lo and behold, they found a transit. This transit had been missed previously because it's very shallow. It's only really 0.6%, significantly shallower than all the transits that have been found before. But it is there. And from it, you can deduce the radius of this planet, and in fact, its composition is somewhat intermediate between these two extremes. It probably has a rocky core, but then a significant mantle of water or water ice. And that brings you into a regime of quite interesting physics, because you can start to wonder what would the conditions be like inside this planet. Inside this planet, the temperature would be quite high, partially because the planet is close to its star, receives a lot of heat from the star, partially because of the sheer pressure of the material above it. This planet has a mass about 20 times the mass of the Earth. And so this is a diagram that shows the behavior of water as a function of pressure and temperature. On Earth, we are in this region of the diagram where three phases exist for water. You've got ice, liquid, and vapor. If you move to very high pressure, the ice phase extends to very high temperature. And in fact, the pressure inside Gliese 436b is thought to be of order a few gigapascals, so it's going to be in this region up here. We call that hot ice, and in fact, it's ice that's denser than water. And so it may well be that this planet has an ocean floating on top of an ice layer rather than the other way around. Now, I'm primarily interested in finding planets which are smaller and potentially terrestrial in nature, because I'm interested in the properties of other planets that might be like the Earth. To do this, to find these planets, you really have to go to space, because the transit of such a planet in front of a star like the Sun would be less than 1 part per 10,000. It's a very tiny effect, and we just cannot measure that precisely from the ground. There's another reason you have to go to space, and that is that the transits only occur once per year of that planet. That's once every year. You can't afford to miss one just because the weather was bad or it was daylight where you happen to be observing. And finally, these transits for these planets which are further out from their star start to last as long as a night or maybe even more, so you really could not observe them from Earth. So the first satellite that was sent up specifically to look for transit is called Corot. It's still in operation today. It's been operated since 2007. And just to show you how the process goes, this is an example of a light curve, so a plot of brightness as a function of time for a star observed by Corot. And it's taken over approximately 5 months. And you can see these variations. They're of order a few percent, and they are actually due to star spots on the surface of the star. Mitigating the impact of these star spots on our ability to find and study planets is actually what I spend my daily work hours worrying about. And you can, luckily, these star spot related features evolve on relatively slow timescales, which are to do with the rotation of the star, and in this case, the rotation period of the star. You can see the same dip coming round here, here, and here. It's about 24 days. They're fairly smooth, and we can filter them out, and we are left with this red curve. Now, in this red curve, there are actually transits of a planet. You can't see them because individually they're impossible to detect. But the planet actually transits its host star every 20 hours. And so there are 192 transits. When you stack them together, they do become visible and clearly detectable. And so this was the 7th planet detected by Corot, so we called it Corot 7. And so the transit is only 3 parts per 10,000. So it has a radius which is less than twice the radius of the Earth. It really is a truly small planet. It's been very difficult to measure its mass, however, because the star is so active. And in fact, there are people at the University of St. Andrews who are actively working on a data set that's been collected since to try and measure its mass more precisely. It's actually an issue of hot contention, and so depending on who you talk to, you'll see a different mass range quoted for this planet. At the moment, it's compatible with both primarily rocky composition and a slightly lighter composition with a significant component of water. Now, in 2009, Corot's younger and better brother, if you like, was launched, which is called Kepler. Kepler is a NASA-led satellite that has a somewhat larger mirror. The mirror of Kepler is 1 meter across. And it has this huge detector at the focal plane, which observes an enormous fraction of the sky. Well, it's only 0.02% of the whole sky, but it's actually a huge area in terms of square degrees. It's 110 square degrees. And within these 110 square degrees, it's continuously observing 150,000 stars, for which it's collecting 1 data point every half hour, and the precision is absolutely pristine, in large part because, contrarily to Corot, Kepler is not orbiting around the Earth. It's actually on an Earth-trailing orbit, so it's in the same orbit around the Sun as the Earth, but it's somewhat behind the Earth. And that means it's in an extremely stable environment. It doesn't move in and out of the Earth's shadow, for example. That allows the photometry from Kepler to be extraordinarily good, and this has led to the detection in the Kepler light curves of, well, to date, close to 2,500 transiting events. This diagram shows a schematic representation of the 1,500 that were detected in the first year of Kepler data. And so you've got each of the stars is shown to scale with its planet, or in some cases there's more than one planet, and the color coding corresponds to the temperature of the star, and this is the Sun with Jupiter in front of it, shown for comparison. And you can see there's this bewildering array of different sizes of stars and planets. I'm just going to zoom in a little bit so you can see a little bit more of detail. So you can see some systems have 3 planets, and if we see the 3 planets transiting, an important fact is they must be very close to being in the same plane. Much like in the solar system, the planets are very close to being in the same plane. Some of these planets have relatively long orbits, so orbits which take several months to complete, so we are getting closer to detecting, and some of them are in what we call the habitable zone of their host stars, which means that if we compute the temperature that would be on the surface of these planets, it's somewhere in the region where water would remain liquid on the surface. That is thought to be an important factor for life to arise, because we think water was the solvent in which the initial chemical reactions which led to the formation of complex molecules in life took place. So this is one of my favorite diagrams, publicity diagrams coming out of Kepler, and it's an animation of, it's in real time, so this is time in days, and it shows all of the multi-planet systems found by Kepler in its first year of operations. And they're all color-coded, so you've got 2 planet systems at the bottom, 3 planet systems, 4 planet systems, and there's even a 5 planet system up there. And these are absolutely fascinating. They are teaching us a lot about the way in which planets form. Again, we find that small planets are found primarily in these multi-planet systems. On the other hand, if we have a giant planet close into the star, we don't tend to find any others, at least not transiting. And that's telling us that probably when a giant planet comes into the inner part of the solar system, it has a very disruptive effect on everything else. Quite what brings them in is still an object of important debate. One of the very interesting things that happens when you have transits by multiple planets is that the timing of the transit is not perfectly periodic, because the planets pull on each other, and this is exactly the same phenomenon that led to the discovery of Neptune. The orbit of Uranus around the Sun was disrupted by the presence of Neptune. Now we can actually use these transit timing variations to measure the masses of these planets without having to resort to the radial velocity method. And that may well be the way in which we first measure the mass and size of an Earth-like planet. In the next few years, it's very likely to happen. Now, there's actually an opportunity for members of the public to get involved in the search for planets with Kepler, and that's the Planet Hunters project, which is a joint collaboration between Oxford and Yale University in the US. And if you're interested, I'd very much encourage you to go and have a look. It's a fun thing to do. Basically, users are presented with a set of likers from Kepler and asked to say if they think they see transit-like events in there. I spend most of my time developing automated algorithms to try and do just that, but there's no way we'll catch them all. And there'll always be some pathological stellar light curves in which we fail to see a transit that a human will see. And in fact, the first confirmed planetary system discovered by this Planet Hunters team has been announced a few weeks ago, and it's a very puzzling one. It's a second binary planet, so the planet orbits a pair of stars, goes around both of the stars, and it transits both of them. But then, following up this system with radial velocity observations, they found there's actually another pair of stars, which is some 1,500 astronomical units away, and these 2 stars orbit each other, and the 2 pairs of stars orbit each other. So it's a really complicated system. It's absolutely fascinating. And systems like this might actually be more common than you think. Most stars are members of a binary system. The Sun doesn't appear to be, but most stars are. Now, relatively few stars are members of a close binary system like this one, but nonetheless, it's a very important category of planets. I'm going to take a slight detour now and talk about a kind of transit that's much closer to home, and that's the transit of Venus that occurred in June this year. I was very fortunate to go to Sweden and observe this transit as part of an expedition organised by a London-based organisation called Super Collider, which tries to foster interest in science from artists and people who work in creative industries. So I was there with a bunch of artists, illustrators, photographers, filmmakers. It was a great experience for me. And this is a picture I took using a small telescope with a rear projection device. And you can see the transit of, well, this is just before Venus exits the disk of the Sun. The first observation of this transit dates back to 1639, Jeremiah Horrocks. But it was Edmund Halley, really, who first made the point that it could be used to measure the scale of the solar system using basically a parallax effect. And sadly, he didn't make it to... he didn't live until the next transit after he'd made this prediction. But there were very successful expeditions set up to go and observe the next two transits, which took place in 1761 and 1769. And this is the expedition as part of which Captain Cook went to Tahiti, went on to explore Australia and New Zealand. This is a diagram made from Philadelphia in 1769. As well as measuring the scale of the solar system using transits of Venus, the transits of Venus were also used to discover the first atmosphere around another planet than the Earth. And this was done in 1761 by a Russian astronomer called Mikhail Lomonosov. And he detected the atmosphere of Venus. Of course, he didn't have the instrumentation to take a picture like this. This was taken during the 2004 transit. But he saw that there was this small arc of light that goes round the edge of the rim of Venus. Well, actually what he saw was this, a very blurry picture of this, and he also saw a small dark rim when Venus was exiting the transit. He interpreted this as saying that Venus must have a thick atmosphere. There's been a long controversy over whether what he saw was really the atmosphere of Venus or an instrumental effect. It seems to have been solved by a team who recently repeated the experiment with instrumentation that matches what Lomonosov would have had available to him, and who confirmed that he would have been able to see the atmosphere of Venus. Now, transiting exoplanets allow you to measure the properties of the atmospheres of the planets in a remarkable way. By measuring the transit as a function of wavelength, you can measure basically the radius of the planet as a function of wavelength, and that tells you how opaque the atmosphere is at different wavelengths. It reveals the presence of absorbers in the atmosphere. You can also look at the time when the planet disappears behind the star. That's known as a secondary eclipse. And if you do that in the optical, you measure reflected light, and in the infrared, you measure absorbed and re-emitted light. So it tells you about the properties of the surface or of the atmosphere, and it tells you about the heat transfer properties of the planet. And you can also look at the phase curve where you monitor the brightness of the system over a whole orbit, star plus planet together, and you might see a small variation, which is essentially like seeing the phases of the moon around the Earth. And it tells you about the distribution of the temperature between the daytime and the nighttime, and you can infer from that something about the properties of the winds on that planet, which might be redistributing heat from one side to the next. I'm going to go very quickly over the transmission spectroscopy aspect, because that's the one I've worked on. So the geometry is that you have a planet with an atmosphere, your star is coming from way over there, and the observer is way over there. And photons coming from the star, well, some of them might just not make it through at all, but some of them, if the atmosphere was transparent, would reach us. Now, if there are clouds in the atmosphere of the planet, that will simply block light up to the level of the cloud deck. On the other hand, if there are gases in the atmospheres of that planet, you will basically, these gases will be more transparent at some wavelengths than others, and you will see a color signature. And we observe this by observing the transit with the Hubble Space Telescope, for example. This is looking at one particular star that is known to host a transiting planet. We put the light through the transit, we project it through, again, a dispersing element, but this time it's a grism. It gives you a spectrum with much lower resolution, but you still distinguish between the different wavelengths. And we make this measurement in both the optical and in the infrared. We project the light onto the detector, and this is what the image we get looks like. Doesn't look very pretty. What we're seeing here is the light of the star dispersed as a function of wavelength. This is the blue end of the spectrum, and this is the red end. This is the secondary spectrum, which occurs when you have two reflections through this prism. We're interested only in this one. We measure the amount of light along this blue line by summing up all the light. And then we plot it as a function of position along the blue line. And what you've got here is a spectrum of the star. Most of these bumps and wiggles are actually not in the star spectrum. They're to do with the instrument. But the green line is the same thing during a transit of the planet. The reason I've shown you this, might seem rather technical, is to illustrate the difficulty of what we're trying to do. We're trying to measure the difference between the differences of these two lines at this part of the spectrum and this part and this part. So the overall difference, the depth of the transit, is about 1%. The relative effect as a function of wavelength is 1% of that. So it's a 1 part in 10,000 measurement we're trying to make. Another way of looking at it is we measure the transit in different wavelengths, and we try and compare the depth of the transit in all these different wavelengths. And this has been done very thoroughly for a very small number of exoplanets. So here we show the radius of the planet as a function of wavelength, going from the near ultraviolet through the visible and the near infrared and mid-infrared. And the measurements are these squares, and this is a theoretical predictions for what we might have expected to see had this planet been completely free of clouds and contained only the kind of gases that we might expect to see, which are mainly things like methane and water vapor, and in the optical we see absorption by sodium and potassium. What we see is totally different. We see this essentially featureless spectrum with only some absorption by sodium and potassium, and we interpret this as being due to a haze. So I'll just skip through. And there is a very hazy planet in the solar system. It's Titan, the moon of Saturn. The difference between the haze on this extrasolar planet, this hot Jupiter called HD 1897333b, is that it extends over a much larger fraction of the height of the atmosphere. For those to whom it means something, it extends over 5 to 8 scale heights of the atmosphere. So it's a very all-pervasive cloudy layer. It's a very cloudy planet. I'm just going to quickly flash this blog called Exoplanets. For those of you who are interested in what we are finding out about exoplanet atmospheres, it's a blog where we try and post, if you like, digests of relevant papers fairly regularly. And just to give you some future perspectives, ongoing experiments, well, Kepler is in the process of measuring the incidence of habitable planets in the galaxy and many other kinds of planets. It will be done in the next few years. So we will know. We already know that planets are very common, probably more common than stars. Probably any star that you look at, it most likely has one more or more planets. The Hubble Space Telescope is being used very actively to characterize the atmospheres of only a handful of hot Jupiters. And then we have direct imaging instruments which are currently being commissioned on the largest telescopes on the Earth. And they will enable us to directly observe young solar systems. In the next decade, we have some very interesting experiments planned both from space, these are all space missions, and using the extremely large telescopes which are being planned for in a decade's time or so. And they will again enable us to find all the planets relatively nearby to us and characterize them in increasing detail. Ultimately, what we might want to do is to look for signs of life. And that exactly what kinds of signs of life we should be looking for is a hot issue of debate. But ultimately, we are looking for signs that the atmosphere of the planet is out of equilibrium, that there is something driving the planet out of equilibrium. And that might be, for example, the simultaneous presence in the atmosphere of chemical species which would normally react with each other very quickly. We are also starting to find planets very close to home. You may have, if you were watching the news recently, you may have seen this announcement of a planet around Alpha Centauri b. It's an extremely difficult measurement because the star is very active. And it's one with which I'm sure there'll be a lot of interesting discussion. You may notice I've put a question mark. I'm still not 100% sure I believe it, but it's fascinating. And I'm going to stop there and just leave you with this poem by Richard Long, which I rather like, and which I like to think about the Earth in a way that this poem suggests.
ladies and gentlemen, I think you'll agree that was really a stunning lecture by Suzanne. Wonderfully clear, wonderfully well illustrated. She told me at tea next door before we came through that this was going to be a very disappointing lecture because there was nothing really to look at. So it's quite amazing. Some of the headlines I noted down here was journalist discovers new planet. Young astronomers discover new planet during the weekend, and it's obviously, it has been done, it is being done. The frequency of the discovery of these planets is astounding to me. What they're made of and what they do there is another matter. So it's now time to invite the audience to ask you some questions. Yes?
Jupiter is often described as a failed sun. Is the fact that many Jupiter-sized exoplanets have been discovered tells us something about the nature of the solar masses in relation to each other, i.e. that there are many suns that don't end up in a fusion reaction and therefore producing light, and they begin to orbit each other given the relative masses in that region.
So I wouldn't describe Jupiter as a failed sun. There is something fundamentally different between Jupiter and between something which might have the mass of Jupiter but is not in orbit around another star, and that is that Jupiter formed in the disk around the Sun. On the other hand, there are objects which are often described as failed suns, which are brown dwarfs, and these are objects with masses which might be from a few times the mass of Jupiter to about 70 or 100 times the mass of Jupiter. So they're still much less massive than the Sun. We think that they formed by a similar process to the process that forms stars, so by fragmentation and coagulation of a cloud of dust and gas. And we do think that these are very numerous. It's also clear that both stars and brown dwarfs, when they form, have a tendency to form in dense environments, and that when that happens, they will be dynamically linked to each other, and there might be some exchanges and some ejections from groups of stars. So it's not inconceivable for a star that forms in isolation, whether it's a brown dwarf or a fully fledged star, to then be captured by another system. We don't have any clear evidence that this actually happens, but it's not inconceivable.
And just one related question. Given that galaxies, the size and mass of galaxies, warps the space-time in which they reside, and given that this gravity has an impact on the physics of that local region, is it conceivable that different galaxies are in different space-time zones, as it were, that the laws of physics, indeed, will be different in different galaxies?
So there's no evidence that laws of physics would be any different in different galaxies. In a different galaxy, you might have a different environment. It would still be driven by the same laws of physics. But you might... One of the things, though, is that the scales we're talking about in terms, for example, of forming planets are enormously different to the scales on which galaxies are forming. So the kind of galaxies you're in may well have an impact on what kind of stars form and what kinds of planets form through the impact it may have on their chemical composition, which is the result of many previous generations of stars. But the gravitational potential of the galaxy is much, much weaker at our position than the gravitational potential of the Sun itself. And so we don't, it had essentially no impact on the formation of the solar system.
Okay.
Your description of how Jupiters, are they gaseous? When they are so close to the star, I find it hard to believe that they're still being gaseous, like your Jupiter or Saturn or Neptune and Uranus.
Well, if you take a gas and you make it hotter, the only thing it can do is stay a gas, right? So there's no reason for it to turn to any other phase. The reason we think that they are made of hydrogen and helium, like Jupiter is primarily made of, is because that's by far the most abundant element that's available in the environment in which they're forming. But perhaps it may be slightly misleading to call these planets gaseous in the sense that the conditions inside Jupiter, as well as inside these hot Jupiters, are very different from what you might think of as a gas. So the pressures are extremely high, and the density is extremely high, to the extent that the inside of Jupiter, hydrogen does not behave like a gas anymore, but it behaves like a fluid. And in fact, it behaves like a metallic fluid where the electrons are shared among all of the ions. So it's not a gas in the sense that you would think of it, but it's not actually that different. The deep structure of these planets we don't think is that different between Jupiter and these hot Jupiters. The outer layers are probably extremely different.
Next one here.
Thank you very much for a very interesting lecture on almost an exponential rate of development of knowledge.
Absolutely.
A non-technical question. As you begin to extrapolate what you learn, what do you think is the message for us humble residents of Earth?
Well, so anyone who's an astronomer will be very used to the idea of feeling quite small and quite insignificant.
Yes.
And the fact that we are, living on a planet and that there appears to be many other planets, in a sense, is quite reassuring to me. Mainly because as a scientist I tend to rely on the principle that we're not in a special place, and it would make it quite hard to reason about the universe if we were in a very special place. I think we still don't know, we don't have the elements to say how common life and the kind of degree of sophistication of life that we have on Earth is. I think we can say fairly safely now that planets which which have the potential to support life might well be quite common. Planets which have that potential for long enough for life to develop to the point that it's occurred on Earth, that's a more difficult quantity to estimate. I would like to think that there's nothing particularly special. But mainly my reaction to this is it's extraordinary to essentially discover an entirely new component of the universe, which we always knew was there, really, but to be able to access it for the first time in the last 15 years, that's a very, very pleasing, for me, I feel privileged to be around at a time when this is happening.
Suzanne, now that you know there are so many of these planets, can you work out, and you know a great deal about them, you just don't know they're there, you know quite a lot about their properties, and now you know what you're looking for in relation to the kind of spectra that you would expect to find in terms of water on these planets. Can you work out any kind of probability that there might be a lifelike entity?
Well, so this was very famously put in the form of an equation, the Drake equation, which has a number of terms which multiply each other, and all of them are smaller than one.
Yes.
And basically what we're doing is trying to fill in these terms one by one. And so you take the number of stars and you multiply it by the fraction of stars that have a planetary system and the fraction of planetary systems, etc. And so I'm going to be really disappointing and say I still can't put a number on that probability because there's still that term at the end that we really haven't got the first idea.
Yes. But since that formula was put forward, there are many more. There are many more planets. So the probability becomes greater.
Well, the problem is that we still don't know about that last term, whether it's 0 or a very small amount larger than 0. It doesn't have to be very big, but if it's 0, there's nothing else. Now, if I was betting, rather than putting my scientific credibility at stake, then I would bet that there is life. And I would bet quite a lot of money that life is pretty common. What I wouldn't bet so much money on is that complex life is truly common. I just don't know about that.
Okay, that's very interesting. Who's next? Who would like to ask the next question? Yes, in the centre.
Yeah, this is slightly related to the last question. I'm just interested in speculation.
Use the microphone.
Here we go.
Just slightly related to the last question, I'm just interested in speculations. What percentage of stars in the universe would you think have planets? As a speculation.
So we can't say for sure because there's still a large, there's many kinds of planets that we can't see, but we know already that again, the number is contentious, but it's tens of percent definitely have planets, and it's probably much more than half. It depends on who you ask, but it's you know, and then many of those have more than one planet.
Right.
So it's really quite a high fraction, is what I can say.
Okay.
Now, I should say that most stars are actually stars significantly lower mass than the Sun, and we haven't actually been able to survey them in great detail. So that's a caveat to what I've just said. But.
Yes. Yeah, yes. Yeah.
What are the implications of all you've said for Hindus, Muslims, Buddhists, and Christians?
Well, I think I have to leave them to make their own implications. I think that in fact, it's quite interesting. There seems to be a growth in the number of debates on this kind of subject around universities. I see them being advertised fairly frequently. At the risk of making a contentious statement, I think religions have a history of coping with changes in what we know about the world, so I'm sure they'll cope. Well, I mean, religious astronomers have played quite a significant role in the history of this, so we shouldn't dismiss them too readily. But
Suzanne, you did indicate at the end of your lecture that the technology that we're going to be using within the next 30, 40, 50 years was really going to take things forward very much further. What do you speculate will be the kinds of things that we can then do?
In order to be able to really look for signs of life on another planet, for example, one of the things we critically need to be able to do is to separate the light of that planet from the host star.
No.
And that will require probably a space mission which involves formation flying, so that we can either do interferometry on the light from the star, or block out part of the light from the star with one spacecraft and then look at the rest with another. And both of these are extremely technologically challenging. The other thing which will be extremely important is the continued development of better and better infrared detectors, because we think it's in the infrared that we want to make these measurements, and at the moment the detectors that are available are just not quite stable and sensitive enough. We need them to be extremely stable. So there are two areas where a lot of development is going to be ongoing.
Right, there's a question here.
Hi. Quick question. I'm assuming that all the stars that you're measuring are within our galaxy, given that the rest of the galaxies are so small. How long do you think, if ever, we'll be able to detect a planet in a different galaxy?
So actually, there might be a slight exception to that rule. One method to look for planets, which I did not talk about at all, is microlensing. I can see Keith staring at me. And that consists in looking for the effect that a star has. So basically, you're looking at distant stars. There's a star between you and those distant stars. It's bending its space-time potential. Is bending the light from the distant stars. And if that lens star has a planet going round it, that will cause a small perturbation in the light that we see that would reveal the presence of a planet. And it's possible to see that at very large distances. We have already seen planets through microlensing which are, halfway across a galaxy. And there's no reason that we shouldn't be able to see them in the galaxies that are near neighbors of our own Milky Way galaxy at some point in the future. All of the other methods that I can think of, it would become very difficult to apply them if you can't resolve the star from all the other stars. So in most galaxies we'll look at, we cannot distinguish individual stars, or the only individual stars we can distinguish are the very much more massive ones than the Sun, or at least brighter than the Sun. And so in that case, if we can't distinguish individual stars, it's going to be very difficult to look for planets around them.
Any other questions? If not, I'm going to invite Professor Keith Horn from University of St Andrews to say a vote of thanks.
Suzanne, thank you so much. You've taken us on a thrilling journey in space and time, from the discovery of the planets in the outskirts of our own solar system to the the first planets discovered in orbiting stars beyond our solar system, and then to the discovery of the first 1,000 planets beyond, with this wonderful orrery of them all moving around like mechanical clocks. Brilliant. And even detection of the atmospheres of some of these planets and prospects for discovering life on them in the next decade or two. So thank you very much for this very stimulating lecture.